So 3D. Now, I often find it handy to redraw all the different two-dimensional shapes in the 3D diagram. I just find it easy to get my head around the problems, because sometimes three-dimensional diagrams can be deceptive. You start thinking things are collinear and they're not necessarily collinear and things like that. So let's do it via an old HSC question, 2003 paper. So David's in a life raft and Anna's in a cabin cruiser. Oh, geez, good for Anna. She gets the cabin cruiser. Geez. But she's looking for him. So maybe his boat sank and that's why he's in the life raft. Anyway, fortunately, they're in contact by mobile phone. That was lucky. David tells Anna that he can see Mount Hope. So he has hope. You're going to love the sense of humour of these HSC writers. From David's position, the mountain has a bearing of 109 degrees. So fortunately, in his little life raft, not only did he have a mobile phone, he had a compass as well. And go, oh yeah, look, the bearing's 109 degrees. And the angle of elevation, he could work that out. Oh yeah, that's 16 degrees. All these things are very handy if you're ever stuck in a life raft. Anna, on her cabin cruiser, can also see Mount Hope. And fortunately, she also has a compass. Oh yes, but for me, the bearing's 139 degrees. And the angle of elevation is 23. And they just happen to know that the top of Mount Hope is 1,500 metres above sea level. So from that, we can work out the distance and the bearing of the life raft from Anna's position to go and save David. All right, and there's the diagram that they supplied in the particular year. So there's the big cabin cruiser. That's not a cabin cruiser, that's like a huge cruise ship or something. And there's the little life raft. So I like to redraw the different diagrams. I can see there's a right-angled triangle there, HDB. We know the angle of elevation 16, height's 1,500. There's another one there from Anna, so 23 degrees, 1,500 metres. Then, if I'm looking down on the ground, I suppose, so if we imagine the ocean being a sheet of paper, David's here, and the bearing of Mount Hope, so B is the base of Mount Hope, was 109 degrees. And from Anna's position, the bearing was 139 degrees. And so that creates another triangle, and that's what we're trying to find. We're trying to find the distance, so the green line as I've got it there, the distance between David and Anna, and what bearing. So I've called it theta all the way around there. That's the angle we need to find. Okay, well, we haven't got a lot of information on that last triangle. We've got some angles we can work out, but can we get some sides? And this is where these other triangles will come in handy. So BD over 1,500 would be tan 74. So I know BD will be whatever 1,500 tan 74 works out to be. And similarly, over in the other triangle, I can get AB is 1,500 tan 67. So if I place those on our diagram, we now have the lengths of BD and AB. So I've got two sides. All I need is at least one angle. If I've got one angle, I'll be able to use the cosine rule. If I get two angles, I could perhaps use a sine rule. So let's have a look. I'm going to draw another north in over here at B, creating a few parallel lines, and I can use some geometry. Because if I know this blue angle here is 139, so what can I do? Well, NDB plus DB, what I've labelled north double dash, would be 180. We've got co-interior angles, basically. So I know from that DBN double dash is 71 degrees. And I can also work out ABN double dash a similar way, and I'll get 41 degrees. So ABD, well, it is made up of DBN minus ABN. They're all actually the same angle. And so ABD, I can finally work out it's 30 degrees. So we'll go put that all on our diagram. So what we were saying is co-interior angles gave me that angle in there. Co-interior angles gave me N double dash BD. So the difference between the two gave me 30 degrees in there. Okay, I have an angle. I've got, it's not only just any angle, it's the included angle between two sides that I know. That's a cosine rule situation because it's the opposite side I want to find. So, let's put it into the cosine rule. 1500 squared, can't be bothered working out what that is, I'll leave it as 1500 squared. Tan squared 67 plus 1500 squared tan squared 74. 2 times 1500 tan 67 times 1500 tan 74 cos 30. Well, that's nice. There's another 1500 squared there. Once we put that all into our calculator, to the nearest metre, we've got that distance is 2,799. All right, you also wanted us to find the bearing, so the angle. Okay, let's go back to our diagram. I know the blue part there is 139. So if I can find angle DAB, add that onto 39, I'll have the bearing. I can now use the sine rule. So sine of angle DAB will be 1500 tan 74 and, over 1500 tan 74 equals sine 30 over B, rearranging. Now with B, notice I've left it as B. I did not write it as 2,799. 2,799 was an approximation. I want to use the exact value that I worked out here, which will be in my calculator. So I'll use that one to get a precise answer, or more accurate. But it's the sine rule using. So could it be an obtuse angle? So I know it's either 69 degrees 9 or 110.51. So if we use 69 degrees 9, angle BDA is 80 degrees 51. Oh no, actually it is the obtuse angle. Because we can, looking at the length of the sides, we know angle DAB has to be bigger than angle BDA. So it can't be 69 degrees 9. Therefore it must be the obtuse angle. That would have caught a lot of people out that year, I reckon. They would have just gone to their calculator, got an answer of 69 degrees 9, would have been happy with that, and say, right, I'll use 69.9. But as I say, from the other information we have, the length of the sides can't be 69 degrees 9 minutes. But we've got to add that onto the 139 to get the bearing. So eventually we get the bearing of 249 degrees 51. So you can get some really nice problems in three-dimensional because you've got to pull different triangles or different shapes together and to come up with a final solution. Here's one a little bit more recent, 2000 paper. The surveyor stands at point A, happens to be due south of this tower. Angle of elevation is 45 degrees. That's nice. Makes that an isosceles triangle. That was very fortunate. 45 degrees. You beauty. They must have jumped with joy when they saw that angle. The surveyor then walks 100 metres due east. So that's a right angle there. We're going due east over to B. And then measures the top of the angle. And what do you know? It still turns out to be one of our exact angles as well, 30 degrees. The first part of this question, and this is the difference between that last one. The last question pretty much, we had to put everything together. It just said, here's all the measurements. Go and find the bearing. Go and find the distance between the two. It didn't really give you any hints on how to do it. Well, that was back in, what year was that? 1990 something. 2000, it's still a long time ago, 2000. But in the more recently, they tend to break it down into smaller chunks. And it sort of helps you go through the question. So if you can't do one bit, at least you can use that info to go and do the next bit and so on. So the first thing they want us to do, express the length of OB in terms of H. Well, if I look at that triangle, OBT, I know that's 30 degrees. So OB is H tan 60. Probably was just worth one mark, but there you go. Bang, we got that mark. Part 2, show that H is 50 root 2. Okay, if we have a look at the other triangle, there was our isosceles right angle triangle. So therefore AO is also H. And so we could go to our other triangle. Bit of Pythagoras, h squared plus 100 squared equals h squared tan 60. And eventually, once we play around with our equation, there we go, 2h squared is 100 squared, and 100 over root 2, there, we're finally there. 50 root 2. So we used one of the vertical triangles to come up with the expression that AO was also h. Then we were looking at the base of the problem. So it was 100 metres due east and so on. We got that. All right. Calculate the bearing of B from the base of the tower. Okay, let's have a look at our compass. O is the base of the tower. No, B is the base of the tower. And and we got that triangle, 50 root 2 we worked out. We know that one's 100. Whoop, there we go. That's the angle I'm trying to find. Bearing from north, we go clockwise. Well, it's going to be easier to find angle AOB and then subtract that from 180. So it'll be the tan will be 100 over 50 root 2, 54 degrees 44. So the bearing turns out to be 125.16. So we've got a couple of exercises there. Just to mix it up a bit, we'll do the odds in 2G, we'll do the evens in 2H because we don't want the evens to feel left out.